right, so today we're going to talk about converting among representations and then go into some optimization. So as you can imagine, we have equations, we have circuits, we have truth tables we've worked with, and so you can convert from any one of these to the other. So as an example, here is the here's a truth table, and if our outputs, we can have a sum of term converted into an equation. We can also take the truth table, here we go, into an equation. Another example of truth table into, or an equation into a truth table, keeping in mind that we're solving each individual one, and then we get a final function and we create our truth table from that equation. Or another example, truth table to equation. I've mentioned before about parity, and maybe we have this operation where we want to recognize a bunch of parity. In other words, we want to have an even number of ones. If we have A and B and C, we want an even number of ones. So we'll add this other parity bit over here to represent a even number of ones. So let's see, the next in this sequence would be 1, 1, 0. So what do you think this parity bit would be over here? 0. And so there we go. And then finally we have 1, 1, 1. And what do you think this parity bit is to make it an even number of bits would be 1. And if we want to make this equation, well, we can say that we'll take each one of these one by one. Oh, here we go. This is not A, not B, and C. There it is, not A, not B, C. Not A, B, and not C. There's that one there. And et cetera, all the way down to A, B, C. But notice that this is not necessarily the optimal, is it? And we're going to look at a little bit later a way to make this more, a little bit more optimal. Oh, and then you can convert from a circuit to a truth table. We've seen examples of this before. With A and B, you can do the calculation. For example, A and B, there you go, right down there, A and B. And then we have A and B not, so then everything else becomes 1, these become 0. We have C prime, so we could do that intermediate step, and then F, you're going to be doing the ANDing of this column and this column. We're left with just those. So our standard representation of the truth table, we could also use to verify. Remember, we went through the Boolean algebra, but you could also do that with a truth table. So in this case, if we have the two equations, we can do the truth table for A and B or not A, and that is our result. Or you can go to the longer equation, and you could verify that these are the same. You can also determine the truth tables are equivalent if you are comparing two individual equations by simply comparing the truth table of the two. So I look at this and I say, are these equivalent? And the answer is no, because looking at the truth table, you come out and you identify that they are not equivalent. Now, there's also the canonical form, a sum of minterms. And we've worked with what I've called the sum of products. And now this is best observed by an example. And if we have, in this case, F is A, B, or not A, that's already a sum of products, but we can expand it because remember, A, not A can be ANDed with B or not B. If you remember, this was one of our identities. And if you expand it out a little bit further, then you could find out that, yeah, that is actually equivalent to that equation there. Now, it gets kind of complex when you have a lot of variables. And so we're going to look at another way of doing this that's relatively easy. So if we look at this, you can identify G, which is A, B, C, D, but you could also expand it a bit, because since E is not included in there, you could expand it out to A, B, C, D. Remember this identity as well? And then we have a sum of minterms. And then we could compare it with this one here. Now, are they equivalent? Well, let's see. This one looks the same, right? And this one looks the same up there, right? And A naught BCD, oh, that one looks the same, right? And, oh, that's already represented right there. And that's already represented right there. So that could be simplified down, and they are equivalent. But when you have a lot of minterms to represent, you can kind of represent it in this form. In other words, you're going to have a sum of minterms, because this is represented by 0, 1, 1, 1, 1, which is decimal 15. And this is 1, 1, 1, 1, 0, which is decimal 30. And A, B, C, D, E, these are all ones. 1, 1, 1, 1, 1 is 31 decimal. So we could represent saying that our equation H is the sum of minterms 15, 30, and 31. Now, one reason I mention that is because we're going to be looking at K-maps, which actually can use this number for populating inside the equation and for simplifying. Let's see if this is, oh, and then of course we have a situation where you have multiple output circuits. Well, if you have this equation and this equation, is that the same as 2? Well, we have a shared gate here. We have the output from A and B, which is used for function f and function g. So in other words, this gate right here is the exact same gate as this one right here. So when you're doing digital circuits, you are allowed to actually share them. So what I want to do is take a little look at some optimization. So let's take a look at in this particular section where you were supposed to read is optimization, and I'm going to talk a little bit about this. I actually have covered that algebraic optimization, but I want to go into one tool that we have available to us called Karnaugh Maps. And Karnaugh Maps are a capability for you to be able to look at relatively low number of inputs, like it gets a lot more complex when you get above 5, and being able to, using a pictorial method, able to shorten the entire equation. And so you have a function here, and this function is going to be F, A, B, C is equal to, oh, I should say X, Y, Z. A lot easier when it's straight letters. X, Y, Z. That is going to represent this area here. Now, if you figure that it's X, Y, Z, the number 0, 0, 0 in binary is what in decimal? 0, right? 0, 0, 1 is 1. 0, 1, 1 is 3. 0, 1, 0 is 2, right? 1, 0, 0 is 4. 1, 0, 1 is 5. 1, 1, 1 is 7. And 1, 1, 0 is 6. Now remember, I discussed in last class, why do we go like 0, 0, 0, 1, 1, 1, 1, 0? So every time you go a column over, you're changing one bit and only one bit. So in this case, you're changing the Z bit. In this case, you're changing the Y bit. In this case, you're changing the Z bit. And down here, this row represents X of 0 and X of 1. So that would be, as I said, 0, 0, 0, or X prime, Y prime, Z prime. And, oops, this next one would be X prime, Y prime, Z. In other words, as I said, 0, 0, 1. This one down here, X, Y, Z prime, 1, 1, 0. Or this one down here, X, Y, Z, 1, 1, 1. So that's what the cells mean. So if you have an equation like this one right here, you can actually put in, oh, by the way, and you could, so we're going to put values of 0 or 1 in here, and then we're going to group them together. And so we're going to graph it. Oh, let's take this equation right here. All right? Not X, not Y, and Z. X, Y, Z, X, Y, Z prime. Not X, not Y, not Z. So this is our table, right? X, not Y, Z means that we're going to have 0, 0, 1. Would you agree with that? 0, 0, 1. So we'd put a 1 right there. 1, 1, 1. So we would put a 1 right here. See, 1, 1, 1. 1, 1, 0. So we have 1, 1, 0 right there. And then a 0, 0, 0 would go right there. So those are put in those specific areas. Now, the next step will be to draw a circle and group as many ones together as possible that are adjacent to each other. So in this case, we have, oh, and there's zeros in all the other areas, by the way. So in this case, we have this graph, and we could draw adjacent circles around that one and that one. Well, the thing that's exciting about this is, you notice that in this case, it doesn't matter what Z is, right? Z could be 0, and Z could be 1. It doesn't matter. The thing that does matter is that X needs to be 0 and Y needs to be 0. So in this case, we draw a circle around those two ones, and rather than having this one and this one separate, we can combine those together in a quickly identify them in a graph, and it's represented by not X, not Y. And the same with these two right here. So this term and this term can be combined together because they're right next to each other. And in this case, x is 1. And you notice that z changes between there and here, but y is 1. So in this case, this is xy. And so now our formula has been reduced to f is equal to not x, not y, or x prime, y prime, or xy. That was pretty easy. Is this a lot easier than the Boolean algebra thing? Yeah. Don't you love Boolean algebra? Yay. All right. And so, hey, if you want to do this, here's your Boolean algebra. So we had a z plus z prime over here, and a z plus z prime over here. So yeah, it's easier. I find it easier. So let's take a look at this. So, wow. If we have this equation here, x, y prime z, or x, y prime z prime, x, y prime z, or x, y z, or x, y prime, or y z prime. So, we could do all of this, we can pull out x from all, you can go through all this stuff, right? Or you can put it into the K-map, and then you look to say, oh, wow, 1, 1, 1, 1, wow. 4 of them all together. So it doesn't matter what y or z is, as long as x is 1, our function g is 1. Wow, this looks pretty good, right? I want to do these all day instead of Boolean algebra. Now, the problem is, yeah, this could also be this circle and this circle too. That works, right? But what you want to do is you want to draw the biggest circle around adjacent ones as possible. So in this case, there it is, right there. Big old assume 4 or grab 4 at one time. Now, it could also be in the shape of a square. So take a look at this. You have, if you place all of these midterms inside of here, you're left with this big old square that are 4, right? Does it matter what x is? No, x could be 0 or 1. Does it matter what y is? Well, in this case, y is 0 or 1. Does it matter what z is? That's a question. Rhetorical. I actually want an answer. Yes, right? Z has to be 1, and that's what's circled in here. So in other words, our equation now is going to be simply h is equal to z. Now, there may be a case where you have multiple circles that you have to make. So here's one, it is included in all of this where x is. But then there's this one lonely one out here, right? Now I could make this a single lonely circle, or you want to circle as many as possible. So in this case, I will circle that and represent that as not yz, because it's x, it doesn't matter what it is, so it's not yz. And then also x. So there we go. That is our final solution. Now, you could have done this in Boolean algebra, but it is a lot easier. Any questions? Then comes a problem like this. What if j, your function, includes 1s in all these positions, right? Well, this includes those two, this includes those two, and you could circle around this that has that as well. However, notice that do you really need this circle around here? Not really, because you're already absorbing this 1 and this 1 and this 0. So in this case, you don't really need to have that extra circle identified around that. So sometimes, by the way, you have one that just sits out there all alone. So this one right here, which is y or x prime y prime z, cannot be combined with anything else. But ooh, look at this. You could actually combine this one with this one because you could use the edges as well. So the circles must have 1, 2, 4, or 8 cells. 3, 5, and 7 not allowed. And of course 0, that would be just dumb, wouldn't it? Circling all the cells is okay. That means your function is equal to 1. So what would this equation be right here? K is equal to what? Well, it's right here, right? It has to be x is equal to 1. And it has to be such that z is not equal to 1, so z prime, right? And then you have to represent this lone cell all by itself. So that, of course, is x prime, y prime, z prime. Z, sorry. This is not allowed. But how would you do this one? Question?
Why did you get rid of the y in the first part?
Why? Because, look at this. You agree that for these two together, right? X has to be 1. Do you agree with that? All right. So what is y in this position? Y is 1. What is y for this one right there? Or this is 0, sorry. This is 1. So it doesn't matter what y is, but we have to have, z has to be 0 in both of those. So that's why you have z prime there. And that is simplified as far down as you can go. So let's take a look at this. How would you make this work then?
Circle just 2 of the 1.
All right, you circle these two, and then would you just circle this alone? No. You could actually circle these two together and get a simplified term. You definitely have to have an or, but in this case, you know that this has to be z, right? And what is z here doesn't change, but y is not. So we have z, I'm sorry, this is x. So this is x, y not. I like that, why not? And then you would circle this again, and that would be x, z. So it doesn't matter what y is, because in this case y is 1 and y is 0 and y is 1. Now, can this be simplified? Well, you can also call this x, y not, or z. Are those the same? Yes? All right. Can you minimize this anymore? Not really, because you have y and z, and there's no identities there. And you can circle the whole thing. So let's do an example. So what I would like you to do is, let's say I have my midterms as such. This is x, y, z. And I'm going to have this one, this one, this one, this one, this one. Okay, let's say I have that. Minimize that. All right, we'll pause and come back. All right, we are back, and well, you know, obviously this one, right? But then there's one more. Ooh. 4. So it doesn't matter what x is. X could be 0 or 1. And it doesn't matter what y is. But in this case, it is not z. So in this case, this function here is going to be z naught, or in this case, x has to be 0, correct? So x prime, and then what's the same over here? Doesn't matter what z is, so it's going to be y prime. Ooh, tricky, huh? Should I put this on a quiz? No. Yeah. Question?
So if we did the 4 squares and then just circled the single 1.
Ah, if you did the 4 squares and circled the 1, would you be able to minimize it further? Well, this would be, in this case, that would be x, or not x, not y, z, right? And that would be just this one right here. So can you define or simplify that any further?
Can you circle 2 things at once, like you did the first one?
Ah, well, you know, here it is. I got it. I got this circled here, right here, right?
You can have it overlap.
Yeah, I could do, as I said, I could do these 2, and then I could do all of these. So, can this be simplified any? Well, let's see. This is.
Oh yeah.
So what if this were? I'm trying to think of really quick how to which identity to do this. Well, which identity would you do to reduce it? So x, y, z. So it doesn't really matter what z is, z or z prime, right?
So I'm saying the only identity that would work is obviously when you circle the 2, you've got z equals z prime. That would factor out. But
Maybe assignment, I'll leave this for you. Yeah, I think I'll do that. Question? Could you complement this other aspect? Well, you could add x prime, prime, z prime separately, but you know that would minimize there. Yeah, maybe. I'll wait for a quiz question on that. All right? I got a few more to go, so let's go forward. Now, if you have 4 variables for this, and which relies on w, y, and z. So in this case, you know, keeping in mind, you know how I mentioned before about minterms, right? Well, this would be 0, 1, 3, 2, 4, 5, oh, what the heck, I'll go over here, 6, 7. This is where it gets tricky. 1, 0, 0, 0 is 8. 9, 10, 11, 12, 13, 14, 15. So remember what I said before. This differs from this by just 1 bit. This differs from this by 1 bit. This differs from this from 1 bit. The same is true when you have W and X down this side. They only differ by 1 bit for each one. So let's take a look at our circles. So we've circled this. So it doesn't matter what W or X are, but Y and Z need to be 1 and 1. So this is obviously YZ. And this is 2 together. So we know that you have to have W and X have to be 0 and 1. And then in this combination, Y has to be 0. Hence we have W prime, X, Y prime. And as I said before, if you group, oh, look at this, you could group a whole bunch of these together, right? So it really doesn't matter what W and X are, as long as Z is equal to 1, your equation is 1, and there you go, G is equal to Z. Two variable maps exist, but that's kind of silly. So the general K-map method, there we go. Here. Convert the function's equations into sum of minterms form. Place ones in the appropriate K-map cell for each minterm. Cover all ones by drawing the fewest yet largest circles, with every one included at least once. And you'll get to minimize function and OR them together. So here we go. Look at our minterms here. All right, so this looks like a single one, right? So where would that be? 0, 1, 0, 0. 0, 1, 0, 0. So we would put a 1 there. It looks like some of these already have some already there. So here we go. So we have Y is missing here, right? So we have WX needs to be 0, 1. So here we go. 0, 1. And then Z needs to be 1. So that means we have 2 of them. Would you agree that that's what should be done? 0, 1, and then Z needs to be 1. And then we have YZ. So that means YZ is going to be an entire column. How about that? You like that? So if we then circle this, what's it going to be? Well, we'll obviously do this one. And, oh, looks like this one can be circled as well. So again, we're left with the function equals YZ, right? But now we're including only these two, which means not W and X. And in here, it looks like Y is 0, right? So Y prime. Would you agree that that's the minimal now? Yes? There you go. And that's just the animation of everything is going to be put ones in there, and then you put zeros and everything else in circle. All right, let's try another one. So A or to a sum of products. So expand it out. So this needs to be expanded out. appropriate cells. So this is only 3, so you put them in. Now we'll pause and circle and see what you get for me for my minimum. All right, let's work through it. First of all, this one's easy. A, so that's going to be 1, 1, 1, 1. This is a single min term, 0, 0, 0. So 1 goes right there. Then we have, oh, look at this. This is the same thing, right? So B, not C, and it doesn't matter what A is. So B, not C. Here we go. All right, so how many circles do I need? Well, you might think I do this one and this one and that one, but it turns out I could do that one and this one. So I am left with simply G is equal to A, or what changes? Well, it looks like C is not C, right? So what do you think? Does that look good? Am I right? Let's see. There we did that, there we did that, there we did that, and those are zeros, and you cover the ones. There we go. Woohoo! We got it right. You're a winner. Good for you. How about this? Go ahead and do this one, and we'll come back. All right, really quiet. So let me just show you what I would do, and then I'll take a question. Ooh, this is tricky. That, and that, and that, and that all together is 1. Is that tricky or what? So what's the difference? Well, up here, it looks like it doesn't matter. You know, this is 0, 0 here, and this is 1, 0. So what doesn't change? B is going to be a naught, right? Same as over here. Well, that's in the row. So in the column, what doesn't change? Well, in this case, C is 0 and 1, but what doesn't change is D. So this would be D prime. Or, obviously, we need to circle this, and that turns out to be A prime BD. And this is where, oops, the last one is a little bit tricky. We could circle 1 here, or we could circle these 2, or we could circle those 2. And in this case, I'm going to do this circle. So that is A naught B. And then what doesn't change here? Well, C is going to be on. All right? Does that look good? I hear lots of murmuring. Murmur, murmur, murmur. Let's see if I got it right. So, yeah, come on, put it in there. There we go. And put it up there. Put it over there. One more there. Right there. And then circles, zeros, and then he's going to cover all the ones, circling. And then we can do that. Ooh, funny looking circle. These in the corners. Remember that they're adjacent. All right, we had somebody in the back with a question. No longer have a question? All right. And then we write up the equation. You think you could do this on your own? Now there are situations where you have don't care. This will come up in later, but I'm not going to go into it in great detail. So, for example, we might have those min terms there but we don't really care what the other two midterms are. So what we can do is you can actually, rather than having a single circle, you can, circling a single bit, you can circle two. And this could be not Y, not Z, or you could just as well have done the other one as well. But the thing is, you don't need both. So don't care is a concept that is not 1, it is not 0, you don't care what it is. And we're going to see examples of this later when we do other combinational circuits as well as sequential circuits too. So let's say we have these minterms here. Not A, B, not C. So not A, B, not C. That means we put 1 there. A, B, not C. A, B, not C. Right there we go. And then not A, not B, C. Not A, not B, C. Right there. And then we have a don't care at not A, B, C. Not A, B, C. Well, that works out nice. And A, B, C. Oops. These would be X's here, not a 1. All right? So, what works? Well, after you place all of these in, ooh, what did I get wrong here? Oh, ABC, I put it in the wrong place, sorry. Oh, I put it over here. That's kind of bizarre. Sorry about that. So, you know what I'll do? Yeah, you do exactly this. So what's the easiest, nicest, cleanest circle? You have one of these, right? And then we have to absorb that one over there. So based on the nice big circle, there's a B, and then there's a not AC. And so our final equation, not AC or B. Introduce don't cares with caution, because you have to really make sure that if you output a 1 here, it doesn't mess up something later on. Or if you put a 0 here, it doesn't mess up something later on. That's usually put it in there when you never see a situation like this would never occur. Let's see. This is an example. Go ahead and look at it online. And if we have a situation automating something, or we're trying to identify how to minimize, you could do that, you could do that, you could do, there's all a bunch of ones you can circle, right? And you might come up with 4 terms, but a better one would be to use only 3 minterms and circle those like as such. So in other words, draw as many circles as you can that are the biggest circles possible, and try and minimize the number of circles you do. If you in this case, notice that you're circling that twice and that twice. This is something you learn by looking at it by eye. And with that, let me see if I want to go over this. That's all I want to cover today. Thank you very much.